tough subject. So if you're seeing my screen, you see that there's an elastic balloon, fires balloons at an angle of 38 degrees north of east. So from yesterday, we know that east is to the right, and then north of east, that means an angle rotation, and that's 38 degrees, and the velocity is 25. And this is shot up and comes back down, okay? Hits the ground over here somewhere. Now, a lot of things that go into this question, just for review here, do you recall how to find the x and y components of the initial velocity?
Yes, so it's up to 25, it's up to 38, and then v of x, v of y. And I remembered that in this case, it would be something like, would you put out as for x 25 cosine 38?
25 cosine 38, and then Vy is 25 sine 38. And these are numbers, so you can calculate them if you want. They are needed in the problem, but that's great. So we got to figure out what it's asking for. It says how far away the balloons are from the launcher when they hit the ground again. So they're asking for the horizontal distance.
All right.
Okay. And I said yesterday, and I bring it up again here, like time is super critical. You got to find time. Okay. So we need to figure out the time here. Which direction do we use to find time, for horizontal or vertical?
Didn't we use horizontal last time?
Okay, so we use them both. The horizontal equation is x as a function of t.
Oh, never mind the y.
Yeah, plus, I'm just going to continue writing this out, t plus 1/2 acceleration in the x direction times squared. So this one, the problem here is acceleration to x is 0, that's 0, but we don't have time. So we know that we need time. So we use the vertical, almost always use the vertical equation for time. All right.
All right.
So that means we're going to go y as a function of t equals y naught or y0 plus y initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. And we know that acceleration in the y direction is minus 9.8.
True.
It starts at 0, starts at ground level. We know that. So we know that y of t equals the initial velocity in the y direction. We just set that up here on the right, 25 sine 38 times t minus 1/2 times, plus 1/2 times negative 9.8 t squared. You can get a number for this 25 sine 38. We do need it at some point.
Like we set it up as like, here it would be like t equals 25 sine 38 over, was it 4.9?
Yeah, I'm going to go through the steps here just because this is our first problem today of getting the numbers out. So now, the reason you can do what you just said is because we're trying to figure out where to hit 0. Okay.
Yeah.
And 0 is here, and then we factor out a t, 15.392, or like you said, 25 sine 38 minus 4.9 t. We set each of these equal to 0. Well, the first one's t equals 0. That's when we started. That's not super useful. And then 15.392 minus 4.9 t equals 0. Like you just said, t equals 15.392 over 4.9. Your instructor expects you to be able to replicate this. Like they don't want you to just go down to this every time, because what they can do is change the problem slightly, and then you've made the mistake of thinking, oh, I got it, no big deal. So what does this become?
In this case, I'll calculate in my calculator. All right, so I got 15.392 divided by 4.9, and so I got 3.1412. So just 3.14.
Sure. The but this is kind of like geometry in the sense that like this is not the final answer. This is an intermediate answer. Geometry is
Mhm.
full of these things. This is not even what it's asking for. It doesn't ask for time. It asks for how far
How
away,
way?
but you need time. So you've done a lot of work. I mean, if I scroll through here, it's a full screen and you're not done. You have to use that X equation, the initial velocity in the X direction times time, to get what's called the range. So X of t, this is simplified, is initial velocity in the X direction times time. And we know that to be 25
Times 3.14.
Cosine 38. Why am
Oh,
I
never
adding that
mind. I
in
forgot
there?
about that. Oh yeah,
Yeah,
because of the
times 3.14.
All right, so we got our 25 cosine 38. And then we multiply that by 3.14. All right. All right, so we got 25 cosine 38. Multiply that by 3.14. And that's 61. This should be 61 meters, right? Yeah, 61
Yeah,
meters.
I gotta catch up to you. I'm on another. Yeah, 61.9 meters. Okay. Um, the summary statement is that if you don't have time, if you're not given time, then you have to find time. It's kind of reasonable, I would think.
Yes, of course.
Okay, can we move on to the next question, or do you have any follow-ups from this one?
I have no follow-ups. We can
Okay,
move on.
I'm going to what I'm going to do is copy in just the prompt, and each of the questions we're going to look at from we're gonna get to all of them obviously, but what I want to do is kind of set this up so you can see why we're what this looks like a question where they ask you everything they can possibly ask. So football is kicked at 37 degrees to the horizontal, 20 meters from the ground. How far did the football travel before hitting the ground? So there's also a bunch of other questions here. So let me try to describe what's happening here. So again, kind of this is your axis. The football goes up, comes down. It has an initial velocity of 20 meters per second. The angle is 37 degrees and hits the ground sometime later.
Mm-hmm. And
The
we don't know
max,
where.
we don't know where. So there's the distance. Like a reasonable question you could be asked is what is the distance? Then you could be asked for the max height. That's what that is. The time of travel, that time is kind of over here. How far away does it hit the ground? That's what it's asking for. That's the travel. You could it doesn't ask for it. It could ask you the time here, where it has a maximum height. You could even ask the distance there, but there's a lot of things you could ask. Parts D and E, which we're going to get to, they are asking things that are new in this problem. They're asking for the velocity at the max height and the acceleration vector at max height. So that's a little bit new.
Mm-hmm.
So what I want you to do, because this really isn't any different than the previous problems, I want you to try to find the time for me.
The time. All right.
The
So
time that this thing is in the air, because the time is used to find the maximum height.
I'll label this all out. Why is it 37 degrees? And this is 20 meters per second. The previous problems we had. Vy.
Do you need a little more time to find the time?
Just a little bit more.
Okay.
Let's see. In this case, it'd be t equals. All right, I found the time.
What do you got for the time?
20 sine 37 divided by, wait, no.
That's right so far.
Divided by 4.9, and then
Okay.
I got 2.45 seconds, 2.46 seconds.
Okay, so we talked about this yesterday about like reasonableness. I mean, that's reasonable. 20 seconds probably is too long. So 2.46 seconds, great. But that's, if you look back at what it's actually asking for, that's part B. Like, it's not even asking for the maximum. It's asking for the maximum height. It's asking for how far does football travel. But part B is really the first thing that you find. Like, you can't answer the other ones before you do that. Sometimes these questions are written that way, and I don't know why, but you have to find time first in this case. Is that okay? Is that clear?
That's clear.
Like, you got to find time. Great. So now we can figure out how far did the football travel before it hit the ground. Okay. We can do that using the equation in the x direction. So I'm going to snip that in here. Okay.
So x equals x0 plus v0 yt.
V0 in the x direction. Yeah.
T plus 1 half ax t squared. All right. So we got that's 0. And we add 20 cosine 37 and plus
times 2.46.
Oh yeah, I forgot that. Times 2.46 and plus 1 half. Wait, do we not use acceleration in this?
The acceleration in the x direction is 0.
Okay. 0 t squared. All right. Now we can just solve this. 20 cosine 37 and then times 2.46, and we get 39.29.
So that's how far it went. Is that agreed?
Mm-hmm.
Okay. So what is confusing for students, I think everything we've done so far has been very straightforward. You find the time, you put it back into the x equation, you find the distance. Part A says, what is the max height? So the height is always governed by the y equation. When you're asked for height, that's y of t. And that's the y naught plus v naught in the y direction times time plus 1 half acceleration in the y direction times squared. It may look like there's more than one variable, but this is a function of t. Okay.
Okay.
So what that means is if you give me a time, I give you a height. Time in, height out. Time in, height out. We need to know the time here where this happened. So just like to find the horizontal distance, we need to know
Do we
the
need to
time.
cut the time in half?
We are going to do that. Why is that allowed in this case?
Because you're looking for the vertex, and that's halfway.
It's halfway because it starts at ground level. So if it doesn't start at ground level, we can't use that.
Oh, I see.
So part A is asking for the max height, and I'm going to just paste this equation in, and you just said it. It's halfway between. So the t here, the t is equal to half of the total time. The total time is what you found in Ben to start out, which was the 2.46. Yeah. So it's 1/2 of 2.46, which is 1.23. So that's the number we have to put into this equation, y of 1.23. But let's do a little bit of cleanup here. Like y0 is 0. We know that the acceleration in the y direction is minus 9.8. We know that velocity in the y direction is 20 sine 37. So all of a sudden, the equation looks a whole lot better. It's y0 is v0. I'm sorry, y0 is 0. 20 sine 37 times time plus 1/2 minus 9.8 t squared. So this looks a lot better. Actually, let me just put a t here. So y of t simplifies to 20 sine 37 t minus 4.9 t squared. So hopefully you see that t is the only variable. T is the only variable. Okay. So you're going to put 1.23 in, and you're going to tell me the output.
This will end up turning into 7.39.
All right, so I can't say yes or no. I'll just say that that's right. You mean it's a calculator step at this point. If it's critical for you to have the correct answer, let me know. I can plug it in.
I'll plug it in again just to double check. And we got 1 divided by 2 and times. All right, it's still the same number, 7.39 feet. Well,
right,
meters.
Great.
Meters.
Great. So we can go to part D, which says find the velocity vector at the maximum height. So we got some new equations now. Finally, we haven't had any for a while, but we got some new equations. The maximum height. So the velocity.
And then for how far away does it hit the ground? Do I just multiply that by 2? 7.39 by 2?
No, we've already calculated that. That's the x direction equation. How far did the football travel before hitting the ground? It's
3.29 meters.
Well, I thought it was 39.29. 20 cosine 37 times 2.46.
Oh, never mind. All right. So C is 39.29. Okay.
C is the same as the initial question that it asks. How far did the football travel before hitting the ground?
Okay, I see.
How far away does it hit the ground? It's the same question. For whatever reason, that's the way they designed this question. Okay, so the velocity It has a new equation. Okay, its equation is the velocity at any time as a function of time is equal to the um, initial velocity plus 2 times acceleration times time. Have you seen that?
I think so. Yes.
I'm sorry. I'm sorry. There's not a 2. It's a mistake here. I'm thinking of something else. This is a new equation, sort of.
Is
It's
v
velocity.
zero plus 1/2 at?
It's at. It's just at.
Okay.
Hopefully you've seen that.
I think I have. Yes.
Okay. Now there's some things though that happen here. So there's kind of like, well, there's one thing you go in when you're going in the x direction, and there's another thing going in the y direction. Do you remember one of the differences between the x direction and the y direction from the original? X equals x naught plus v naught t plus 1/2 a t squared.
Is it that x doesn't have an acceleration?
Bingo, that's correct. So the velocity in the x direction is the initial velocity in the x direction, always. So remember I said, like, if you ever jumped off into a pool, or like anything where you've jumped off something forward, your velocity forward is the same. That is never changing, but the gravity is pushing you down, but you're still moving forward at the same velocity.
All right.
Maybe that doesn't make any sense, but so in the y direction, the velocity is the initial velocity in the y direction. We know that acceleration is minus 9.8, so it's often written as minus gt, because this is g.
Oh, I see.
Okay, now, rather than me putting in a number, but g is well, here it's not quite right. It's plus gt, but g is negative 9.8. So sometimes, and I don't write this, it's v0y minus 9.8t. Like sometimes that's the way it's written, and that's fine too. Okay, so is that okay? Do you understand that it depends on which direction you're going, which equation you're using?
Yes, it does.
Okay, so the maximum height, this right here, both of these are functions of time. Do we know the time when it's at a maximum height?
The maximum height, 1.23 seconds, right?
1.23 seconds. We also know that the initial velocity in the y direction,
That is
20 sine 37 minus, notice there's no t here, minus 9.8 times 1.23. So I'd like you to calculate that, please.
20 sine 37 minus 9.8 times 1.23. All right. 20 sine 37. I get negative 0.01.
So basically 0.
Pretty much, yeah.
Yeah. So it's supposed to be 0, okay? And there's a reason why. If you throw a ball up in the air, like if you throw a ball straight up, there's a moment in time where it just sort of stops.
Yes.
It doesn't really stop, but it's neither going up nor going down for that like instantaneous amount of time. So the question that's being asked here, part D, it's a conceptual question. Conceptual questions are questions where you're supposed to know the answer without doing the math. The velocity vector at the maximum height, the velocity in the y direction is always 0 there, but not x, but 0. But y is always 0, meaning it's neither going up nor down at that point.
All right.
Okay, but there is an x component to it. Like it has an x component to its velocity. So the velocity in the x direction,
I'll just be 20 cosine 37.
yes, 20 cosine 37. And it's the same no matter where you are. It's always the same.
All right. So we get for v of x will be 20 cosine 37. And I'll calculate that 20 cosine 37. That's 15.97.
But that's the same as its initial velocity. So no matter where the projectile is, whether you're going up or coming back down, its velocity in the x direction is always the same. So these arrows I'm drawing are meant to indicate that it's always the same.
It's always constant? Yes.
Right. But the velocity in the y direction does change size as needed. And we're not going to talk about that, but that's what's going on here. So part E, maybe, and I hope you this is kind of slow. Maybe it has that appearance. I don't think that is. This is there's like a lot of concepts we're covering right now. So it's not, it's worthwhile to do it in this much detail.
Yeah, I'm not saying that that it isn't useful. I appreciate it.
Okay. So we got the same issue in the x direction and the y direction for acceleration. So in the x direction, the acceleration is always 0 for projectile motion. For these problems where you shoot something in the air, or you throw something off a cliff, or something like that, projectile motion, it's always 0. In the y direction, it's always g.
Oh, okay.
Meaning it's always minus 9.8. It's always constant. So your exam, whatever you got coming up, this is the type of conceptual question your instructor might ask. What is the acceleration in the x direction for projectile motion? 0. What is the acceleration in the y direction for projectile motion? Minus 9.8. It's always these numbers. So these are absolutes. These are things that like there's nobody's disagreeing on.
That just doesn't change.
Just doesn't change.
Fair enough.
Okay, so move on to 9.
Yep.
9 refers to something else. Maybe it's on the second image you sent. It is. Okay. Hooray. How's math going for you?
All right. It's easy so far.
Good. I like hearing that. A projectile is to be launched at an angle of 30 degrees. So this figure should look very similar to the ones that we've been drawing. You agree? Like we've been sort of drawing these where they go up and down, and here's V0, whatever. It falls beyond, so that it falls beyond the pond of length 20 meters as shown in the figure. What is the range of values of the initial velocity so that the projectile falls between points M and N? Is there anything else?
So we're finding the velocity?
Yes. So basically, it's really two questions. The first one is, what's V0 to land at M, big M, and then what's V0 to land at big N, sorry. So what is the distance to go to big M?
Looks like 30 meters.
Right, and big N is 40. 40 meters. Okay. This is one of those working backwards questions, meaning that we're used to being given the initial velocity, and then we find the time, and then we calculate how far it went. Here we don't have the initial velocity, but we know how far it went. So what can we do? Okay. What would you start with? Where are you kind of leaning to start here?
So we're looking for M and N. Look for the velocity?
We are trying to find the velocity, but so like what I'm trying to get you to do is start. And I'm asking you to take a step. Okay. And what I mean by that is like you've got to try something.
Try to find the time.
We would like to find the time. So let's see if we can find the time. Which equation do we use for time?
Usually the horizontal. No, vertical. Y.
Exactly. So let's write that down. Let's start. Let's take a step. Let's try something. Y equals y naught plus v naught y t plus 1/2 acceleration in the y direction times time squared. We know that it's starting at 0. We know that acceleration in the y direction is minus 9.8.
Yeah.
The initial velocity, though, in the y direction, if we draw this triangle, we're used to being given this number. So this right over here is v0 cosine 30 degrees. And this up here is v0 sine 30 degrees. But we're used to having that number, right?
Yeah.
So
But we do have the bottom number, though. We have 10 meters.
That's not a velocity. This is a distance.
Oh, never mind.
Okay. So here's what we have. We have y equals v0 sine 30 times time minus 4.9 t squared. What's the problem that you see here? Because there's a problem.
There are two variables in there.
Exactly. So we have this issue of like, well, normally we're given that, so that's no good. We do know the following though. Y is 0 when it hits the ground. And if we factor out a t, v0 sine 30 minus 4.9 t, we know that t is 0 or t is equal to, v0 sine 30 over 4.9.
Oh.
But that's
Okay.
no good either because again, like we don't have v0, but it's something. Now, physics is hard. It's different than anything you've ever taken before. You will get credit. You will get credit by doing this. Like if this is all you can do, you get credit. I mean, I obviously want you to do better than that. But I will. I want you to be able to do the whole thing. So we'll see. The next thing here is if you had the time, what would you do? You would plug it into the x equation. So the x equation is x0 plus v0 xt plus 1/2 acceleration in the x direction t squared. But we know that its initial x position is 0 and its acceleration in the x direction is 0. So we know that x equals v0x times t. The v0x has the same problem as before. It's v0 cosine 30 times time. What is the value of x in this equation? Well, that's what we've got up here. Our value of m. That's how far it went.
Mm-hmm.
So we have that there. So we know that that's 30 equals v0 cosine 30 times t. And notice we have an equation up here. We can bring that down there.
Oh, put in for t.
2 equations, 2 unknowns. So even though you can't find t, you still try to find t.
Mm-hmm.
Meaning like you have an equation for it and you can use it. So we know that 30 equals v0 cosine 30, v0 sine 30 all over 4.9.
So this turns to like 30 equals v0 squared cosine 30 times sine 30 over 4.9.
So we're solving for v0. So it's v0 squared cosine 30 sine 30 over 4.9, or in a different order is fine. This part in parentheses is a number. You're going to get that number, You're going to move it to the other side with dividing and then take a square root.
And I got 18.42 for this.
Okay.
18.43, never mind.
So you got V0 as 18.49. We'll just say 18.5. Okay.
Mm-hmm.
Is that one of the things it's asking for? Are you done?
No.
No. That's the initial velocity to get to point M. So to get to M, you need 18.5 start. To get to N, okay, we have to use the distance for that. So it's essentially the same thing, except wherever you see a 30, 30 changes to 40. 30 changes to 40, because that's the only difference. It should be a bigger initial velocity.
Okay, so we put in 40.
Just to be clear, it's the same calculation. Like there's nothing different about it, except this time you're using.
Yeah, different.
Did you get a value?
Yeah, I got 19.95.
Okay, so call it 20.
Mm-hmm.
Okay. Great. All right, that is all 9 is asking for.
Yes.
So we can move on to 10 now.
Yes.
All right, a ball is kicked at an angle of 35 degrees with the ground. That's what we see down here.
Mm-hmm.
They don't give us an initial velocity. They want like sometimes it's even like question mark initial velocity. We don't know that. To hit a target that is 30 meters away at a height of 1.8 meters. So this problem is actually very different than the ones that we've done 1 through 9. 1 through 9 all assume to hit the ground. Here it does not. It's no change for me, but for you it can feel like it's a big time, a leap, big time, like, oh my gosh, this is totally different. It is, but it isn't. Like you're going to use the same equation. There is a slight change in that, but it's the same equations to start with. If I asked you to find the time, which equation are you going to use?
For time, I would use the vertical equation.
Okay, so let's do that. Y equals y naught plus v naught y times t plus 1/2 acceleration in the y direction times time squared. It is starting out at 0. Okay. The initial velocity, though, we don't know. It's v0 sine 35 degrees times time. We know that acceleration in the y direction is minus 9.8, so this becomes minus 4.9 t squared.
Mhm.
Okay, we also know now y is not 0 this time. This is the y value.
Oh. So,
Y is 1.8. So we have 1.8 equals v0 sine 35 t minus 4.9 t squared. How many unknowns do you see in this?
2 unknowns.
2 unknowns.
Time and velocity.
Right. That's bad. I mean, in the past, we at least could get time out of this, but we're kind of in a bad spot here. Because this isn't equal to 0. So the only other equation you have is your x equation. X equals x naught plus v naught t plus 1/2 acceleration in the x direction times time squared. We know that it starts at 0 at the origin. We know that its initial velocity is v0 cosine 35 times t. What is the acceleration in the x direction?
Acceleration in the x direction is always 0.
Always 0. So this is all we got here. Now, we also know that the x value. And you might be saying, well, how do we know that? Well, that's how far it went.
Yeah,
we
the
don't
30
care
meters.
we don't care that it didn't hit the ground because that's what we care about up there. So this is 30 equals v0 cosine 35t. Okay, so decision time here. This is where it's potentially there's some uncertainty because this is different. If you solve this for v0, okay, you're going to have the following. v0 equals 30 over cosine 35 times t. When you put that in here, the t's cancel. That's okay. That works. That actually works out kind of nicely.
Okay.
If you solve it for t, you get t equals 30 over v0 cosine 35. When you put that in this first one, the v0s cancel, but here you have a v0 squared on the bottom.